Hi guys, welcome to lesson 85. This is a little bit of a mind bender. We're getting into some really nice, juicy algebraic, some upper level algebra concepts, and some of them start to get a little mind bendy. So let's try 85. The topic is systems of nonlinear equations. Okay, we've been talking about systems of equations for a long time, and they have always been linear equations because they've had an x and a y, right? And they've been they haven't always come to us in the order y equals mx plus b, but we've always been able to rearrange them to that if we want. But the important thing about linear equations is that they have an x to the first power and a y to the first power, and nothing more complicated than that. So now if we have nonlinear, that can mean a lot of different things, and we've just started to tread out into that space, but it just means we're going to have more complex variables. And I'll show you a couple examples, and you'll see that we'll still be able to use, because they're systems of equations, we'll still be able to use our good friends substitution and elimination as our tools for solving these, but we'll just have to get a little bit trickier in our approaches. So let me just walk through example 85.1 with you. In this example, we have a system of equations, x squared plus y squared equals 9, and 2x minus y equals 3. Now right off the bat, you can see what I mean. It's a system of equations, it's got an x and a y, but dude, since when do we square our variables? We've never done that before, and that's what moves us. This one's fine, this one's a linear equation. This is just an x and a y and a couple numbers chilling. That's no problem. We could rearrange it to look like that. But this is a beast of another color. This has got squares in it. It does not look like that. This is a non-linear equation. So when we solve it, we just have to try a few different techniques. Now the first thing we notice is that, and I'll just tell you this right now, we can't use elimination because these are first order terms and these are second order terms, and we do not want to try and turn these into second order terms. No, that's not cool. So elimination is out, and instead we'll work on substituting. And again, there are different ways you can do this, but because we have just a single y here, let's get him by himself and then see what we can do. So what I'm going to do is I'm going to add y to both sides to turn that negative into a positive, and then I'm going to subtract the 3 from both sides. Let's see what that gets us. That goes away, that goes away. 2x minus 3 equals y. Okay, we're getting closer because there's a y and there's a y. So what if we square this y, square this side, and then substitute that in for the y? See where we're thinking here? Now, so we're going to square both sides. Now, here's the ugly truth. This is a binomial. We don't just get to square the individual terms. We have to square the whole thing. So we have to go 2x minus 3 times 2x minus 3. Draw a breath. Oh boy, here we go. 2x times 2x. 4x squared. Is that what you said, Lydia? You're right. Oh my gosh, that is perfect. Mackenzie, I'm going to let you do this one. 2x minus 3. That's right, minus 6x. Oh my gosh, you're on fire today. Rachel, minus 3 times 2x. I know, it's minus 6x again. Good job. And then, Tori, this is for you. Minus 3 times minus 3. Yes, you're right. It's plus 9. Candy for everyone. You're brilliant. Adding together, 4x squared minus 12x. I'll do this. Plus 9. Okay, this is all equal to y squared, right? I'm just going to rewrite that to remind us. So this big, ugly mess can go in here for our substitution. See, it's the same idea, it's just a little kookier because we've got these higher order equations in our system. So let me slide my paper up a scooch, okay, and let's substitute, shall we? We still have our x squared to start with. Then we have to add all of this gibberish in, 4x squared minus 12x plus 9, and that will equal 9. Sorry, John, I didn't mean to call your problem gibberish. I really love it. Don't worry about it. I'm afraid he's going to smack me down for criticizing his work. Oh, I'm so crooked. There. Beautiful. All right. Makes sense? Now we have a whole long thing. Now we can do some simplifying. And let's get everything over on this side, to the left side of the equation. So let's subtract 9 and subtract 9. And then we can combine those as like terms. 5x squared minus 12x cancels equals 0. Oh, okay. Now let's try factoring this into, let's try, because we can break this down. We can take an x out of both of those terms, and then we'll say x times 5x minus 12 equals 0. Okay, see how I did that? I factored that because we're trying to solve for x. So, what that tells us, I'm going to copy this onto my next page. I heard Emma yelling dribbles upstairs. That's a nickname in our home. I won't say too much more about that. X times the quantity 5x. Oops, I went off the line, but you know what I mean. Okay, so we've solved things like this before. We know that in this case, either x equals 0 or 5x minus 12 equals 0. And remember, that's our little rule that if two numbers are being multiplied together and they equal 0, one or the other of them has to be 0 in order for that to be true. So, x equals 0 is one of our solutions to this, and to solve for this, we'd say 5x, I'll add 12 to both sides, and then we divide by 5. X equals 12 over 5. That's not a very pretty answer, but that's the right answer, all right? So we have solved, what we found is that there are two possible values for x in this equation, and then the final step rather is to solve for each of these values of x. We need to find a value of y. So what I'm going to choose to do is what John chose to do. You know how I like to be like John. I'm going to choose the simpler of the two equations, 2x minus y equals 3. And I'll write that over here, 2x minus y equals 3. I'm going to use this to plug in my x values and come up with the corresponding y values. So if 2x minus y equals 3 and x is equal to 0, then that would be 2 times 0 minus y equals 3. That would be 0 minus y equals 3. Okay? And that just means minus y equals 3. I'm going to divide both sides by minus 1 in order to get my answer. Those cancel. So I find out that y is equal to minus 3. So one pair of points that will satisfy this pair of equations is 0 minus 3. See? My x and my y. All right? And then the other one, I have to do the same thing. I have to use this equation and plug that in. So it would be 2 times 12 over 5 minus y equals 3. All right? 24 over 5 minus y equals 3. This time I'm going to add the y and subtract the 3. So I'm going to go plus y and minus 3 to both sides. Okay, so then I have, that's gone, 24 over 5. Now what I'm going to do is I'm going to convert this 3 to a fraction over 5. And I'm going to make it 15 over 5. 3 times 5 is 15, equals y, and 24 minus 15 is 9 over 5 equals y. So my second pair of points is 12 over 5, comma, 9 over 5. That, my friends, is how we solve a system of equations that are nonlinear, meaning they're both not just simple little guys. I hope you can see that. I'll scooch it over so you can copy any of that you missed into your notes. Go ahead and pause me if you want to collect that, but I'm going to do one more example with you before we finish this lovely lesson. Okay, I'm moving on to example 85.2. I'm waiting to see if any of my cats will put in an appearance tonight. Okay. Example 85.2. Another system of equations that's not quite as linear as we're used to seeing. Let me write these equations down. You guys go ahead and copy them, and then I'll explain why they're so kooky looking. That's t to the subscript d equals 25. Equals 15. Okay. This is a system of equations. The variables are going to be used in our near future in problems that have to do with boats in the water. And the B stands for the speed of the boat, and the T times the D is going to be standing for the time that it goes downstream. Okay, so the B is one variable, T to the D is another variable. Okay, so that's what is tricky about these systems of equations, is that these are nonlinear because we are multiplying variables together. In our old strategy, we never multiplied x times y. So in this one, we're multiplying things. Notice these are 5s, they're not s's, they're kind of confusing. But we have plain variables here, but here we're multiplying, and that's what makes these nonlinear. Now, again, there are a couple different ways that we could solve this using substitution or elimination. But what I notice, and what John Saxon notices, and you know I always copy him, is that these two dudes cancel each other out. So what we're going to do is we're going to use elimination to add the two together. And what we're going to get is that those two cancel, and we get 2btd equals 40. Divide both sides by 2, that's pretty simple. And we get that this variable called btd equals 20. Now, notice that we haven't solved for b or td. Those are our two variables. We haven't solved for either one of them yet, but we've come to some sort of useful information, because what we can do now is we can take this known quantity and we can plug it back up to either one of the equations. I'm going to choose the first one. But if our BTD is equal to 20, then we can say 20 plus 5TD equals 25. See? Because this variable matches to that variable. So I can plug it in. So now we do a little presto changeo with our algebra. Let's subtract 20 from both sides. And let's get 5TD equals 5. Oh, this is going to work out cute, isn't it? So this TD variable, which does equal time downstream, works out to 1. Now that we've solved for one of our actual variables, that makes us very happy. Now we can plug that back into something simple to get a known quantity for our good friend B. And what John suggests we do is let's plug this back into this one. So if B times 1, because B times TD is equal to 1, so we'll put the 1 right there, equals 20, then B is equal to 20. So in our cute little problem, the speed of the boat is 20, the time that they traveled downhill is 1 hour. That makes no sense to you now because we haven't talked about these problems yet, but once again, John is setting us up by teaching us to do the calculation before he explains how we learn how to set these problems up. So once we figure out how to set them up, we'll be super pro at solving them. So again, this is an example of a nonlinear system of equations. In the book, on page 352, he shows an alternative way to solve this problem if you want to adjust the elimination. If you want to look at that, you can. Frankly, I think it just boggles the mind myself. But go ahead and look at the rest of example 85.2 if this process didn't seem simple to you. This seems pretty simple to me, but again, every brain works differently. Use these examples when you're doing the pressing. Oh, here's my, this is my magnifying glass I use to help my eyeballs read the problems in the book, because sometimes those little exponents are too much for my eyes that are still recovering from their surgery. Okay, that's lesson 85, Systems of Nonlinear Equations. I'll see you for lesson 86.